Let's talk about the force of gravity. This is an attractive force of the Earth on an object. It is the downward force of the Earth on an object, and it can be denoted in a number of ways, as we've already discussed. Now, on or near the surface of the Earth, the force of gravity can be calculated by taking the mass of the object and multiplying it by the acceleration due to gravity. And the acceleration due to gravity is positive 9.8 meters per second. Now, to simplify calculations, as you already know, we will typically use 10 meters per second, while in lab, we will typically use 9.8 meters per second. Now, if you take a look, please, at your equation sheet and take a look at the equation now highlighted, I'm going to speak about this during this video. So you've learned in previous videos that the acceleration is equal to the net force divided by mass. Well, in this case here, our acceleration is the acceleration due to gravity, or positive 9.8 meters per second. So if I put that into this equation, I get the following. Now, if I further rearrange this by multiplying both sides by mass, I end up with this equation here, where the mass times the acceleration due to gravity is equal to the force of gravity on or near the surface of the Earth. Now, the direction of the force of gravity, and therefore of the acceleration due to gravity, is always down, because this is an attractive force and it is straight down towards the planet Earth. So you're probably wondering at this point, why are we calling little g positive 9.8 meters per second squared? You're probably saying, well, in the previous unit, when we're using UAM in our studies of kinematics, it seemed like we were always calling little g negative 10 meters per second. And you're correct, we did. Please remember that you are the one that chooses your coordinate system and your inertial frame of reference. So in those problems where we used UAM equations, if we chose to call up positive, then the acceleration due to gravity, little g, was negative for our defined coordinate system. However, for the force of gravity, little g is positive 9.8 meters per second. And remember, if there is a net force, the acceleration is always in the direction of that net force. Also, I want to speak very briefly about this highlighted equation on your equation sheet. This is the equation for the universal law of gravitation. This is something we will speak about later in this unit, later in this course. But I want you to look at it and think about what you're seeing here. Now, we'll refer to this as the big G equation. But if you see here, we have the absolute value of the force of gravity, and that is equal to this constant big G. Now, that is a positive constant. Again, you'll learn about this later. And then that is multiplied in the numerator by mass 1 and mass 2, which are positive values. In the denominator, you see r squared. Well, what that r squared is the distance between two objects, and the distance is going to be a positive value. And having said that, we have the fact that r is squared, so regardless of the value, you will get positive number for the force of gravity. So everything in here is positive. When you calculate the force of gravity using the universal law of gravitation, you will get a positive value. So I hope I've answered the question for you. Let's look at this example here. A 200-gram object is hanging on a string, and it's attached to a spring scale. what does the spring scale read? Now, this is a very simple problem and one that I will often do and demonstrate in class, and at first students struggle with it. So let's talk about it here. We have the sum of the forces. In the previous videos, I've taught you all about free body diagrams, and I also taught you how to sum the forces. The net force is equal to mass times acceleration. Look at our free body diagram. We have the upward force of the string on the object, and then we have the downward attractive force of the earth on the object, where the object here is this hanging mass. Now, when we sum the forces vertically, calling up positive and down negative, as we're defining our own coordinate system, I am going to subtract the force of gravity from the force of tension. Okay, so I'm subtracting my negative forces from my positive forces that I have defined and set those equal to mass times acceleration in the y direction. But of course, this object is not accelerating in the y direction. And we've discussed previously, yes, these forces still exist. There's just no net external force leading to an acceleration. Now, take it a step further. For the force of gravity, now we will put in mass times the acceleration due to gravity. And we set that equal to 0 again because the acceleration in the y direction is 0. Therefore, we can make the statement that the force of tension is equal in magnitude and opposite in direction to the force of gravity, which I've shown as mass times the acceleration due to gravity. Remember, guys, again, we will use 10 meters per second to simplify calculations. So let's go ahead and do that here. Don't forget, guys, your 200-gram object, we need to convert that into the base SI unit of kilogram, which is 0.2 kilograms, multiplied by 10 meters per second, which you recall are the base SI units for the derived unit called a Newton. And when we solve this problem, we get 2 newtons. And indeed, the spring scale will read approximately 2 newtons. An object is at rest on a digital scale, and the scale reads 50 newtons. That is its weight. What is the object's mass? Again, let's look at our free body diagram. Let us define our coordinate system and call up positive and down negative, which means we will subtract the force of gravity from the force normal. Let's look at our acceleration vertically. The object is not accelerating vertically, so therefore the right side of this expression becomes 0 when we sum in the vertical direction, which means we can therefore say that force normal is equal in magnitude and opposite in direction to the force of gravity, which we've shown as mass times the acceleration due to gravity. And that is the weight, and we are told the weight is 50 newtons, which means that the object's mass must be 5 kilograms. And you can look at that this way as well. If we take our 50 newtons here and we divide it by 10 meters per second squared, we will get 5 kilograms as a result. Okay? All right, guys. So the other thing I want to speak to you about before I wrap this up is to distinguish between gravitational mass, which I've spoken about in this video, and inertial mass, which I taught you about in previous videos. Those two have been found to be experimentally identical. So we have the equation for gravitational mass and the equation for inertial mass. And what I want to look at is you can find the inertial mass by applying a force and measuring the resulting acceleration. And you may recall that I used a PHET simulation to do this in a previous video. That's one way that you could experimentally calculate and determine inertial mass. Look at this image here, which is from PHET as well. And this man is applying a 200 Newton force to this refrigerator. And the result is the object accelerates 100 meters, or excuse me, 1 meter per second. Now, using this equation here for inertial mass, you can see in the numerator, 200 newtons, in the denominator, 1 meter per second. And what does that give us? The object's mass, which is indeed 200 kilograms in this case here. Now, you can do this a number of ways. Now, we haven't talked about Hooke's law and springs yet, but if I have a compressed spring and then I release that spring, the object accelerates. Well, I can use equations to determine the force exerted by the spring on the object and that resulting acceleration. That will enable me to also experimentally calculate the inertial mass of this object. Now, let's go ahead and talk about gravitational mass and compare gravitational mass to inertial mass, which again have been experimentally determined to be identical. This is easy, guys. If you want to design an experiment here, let's say on planet Earth, where we are under a nearly constant gravitational field of 9.8 meters per second, then both objects are experiencing that same acceleration due to gravity. So really, what I'm going to do here is I'm going to take an object of unknown mass and place it onto this pan balance. Now, what's going to happen here is you're going to see the pan balance tip to one side. Now, in order to find the mass of this object, I will add masses to the right side of the pan balance. And these are masses that I know their value. So let me add 1 kilogram to the pan balance. And that didn't quite do it. Let me add another 2 kilograms to the pan balance, and that leveled it out. So now we can make the determination that this object's weight must be 30 newtons. Now let me show you how I got that, and that's just using these very simple equations. Again, rearranging multiplying mass by both sides, I can get the value of my 3 kilograms, which must be the mass for the unknown object. It's unknown mass. It must be 3 kilograms because under this same gravitational field strength, they are balanced. So the 3 kilograms multiplied by 10 meters per second will give me the weight of the object, which is 30 newtons. Okay, so in this video, I've taught you how to design experiments to compare gravitational mass to inertial mass. And of course, you're now able to apply force is equal to mass times acceleration to calculate gravitational forces on objects. And I'll see you guys in class.